Okay, so before going into describing the algorithm for shortest path, we need to prove properties of the optimal shortest path. By the way, this is the regular tactic when developing algorithms. You want to compute something, you prove some properties of this entity that you want to compute, and you use those properties to derive an algorithm. So shortest path have this very nice property that if you have a shortest path between two vertices, okay, U and V, and you pick any two vertices in the middle of this shortest path. So pick a vertex here and pick a vertex here. Then the subpath, right, the portion of the path connecting those, maybe I should use the other kind of marker, if I can figure out how to do it. Here we go. The subpath connecting those two vertices, this yellow portion marked in the path, must also be the shortest path between those two vertices, right? So if this is, oops, and that's where this thingy stopped being useful. Let's try again. So if this is vertex X and this is vertex Y, right? Then the shortest path between X and Y is this subpath marked in yellow in the drawing. And the reason is very simple. Let's assume this is not true. Let's assume there is a shorter path. Okay? If there was a shorter path between X and Y, then there would be a shorter path between U and V, right? You would go from U to X following the old path, then you would go on the shortcut we just wrote down, right? The red shortcut, and then you will continue from Y to V. And you will get a shorter path, but that's a contradiction because we assume we have a shortest path. So this behavior of shortest path, that any subpath of them is also shortest path, is an extremely powerful property. Here's the proof in words, but it's completely useless in my opinion. Here is another drawing of the proof if you want more nicely drawn, just repeating the same argument I just made. For our purposes to prove the algorithm and develop the algorithm, we need a slightly weaker property, which is essentially the same property, which says that if we have a vertex U, and we have now the vertices, I guess vertex S, not U, S, and we have vertices V1, V2, V3, right? V4 and so on, right? We have all those vertices, then, and we look on the distance from S to V1, the distance from S to V2, and so on, then first those distances are of course monotonically increasing because we are speaking about edges that have non-negative weights, but more importantly, for every such prefix path, let's in this case from S to V4, this prefix path must be the shortest path between S and V4. And of course, this follows immediately from the previous claim. And this is the property that we'll need, right? So a prefix of a shortest path is a shortest path. This is the easy way to remember this observation that we need. And at some level, this is all we need to make a shortest path algorithm efficient, which is kind of